Hey and welcome back to the lab. And today here on the bench we have a Yeasu FT-60, which is of course an handheld radio, and this radio suffers from a sensitivity loss on 70 centimeter and 2 meter. So let's look into that and let's see what we can do. Okay, and I've already prepared everything so far that we can just start. And so as you can see, we are on 2 meter, and indeed something is wrong here with sensitivity. First let's look into our specs, and then let's go over to the service monitor to show what I can see here. And here we have what we need to see, so that is receiver sensitivity, and I zoom in here a little bit, and we are talking about 140 to 150 megahertz FM, and you see sensitivity is with 0.16 microvolt for 12 dB SINET or better. So that means I've set the service monitor to exactly 160 microvolt, and we should see minimum 12 dB. And the same we have to do on 70 centimeters as well. So that is down here. And there it is a little lower sensitivity, so with 0.2 microvolt we should see 12 dB SINET or better. So let's go over to our service monitor. Okay, and here you see we have all the important figures, and I've set, as already set, our input signal strength to 0.16 microvolt, and normally we should see here at our SINET figure 12 dB or even better. So normally it is always a little better than the specs, but here you see that the signal is not really getting through. And even when I increase here the level, so you may hear in the background that there is something, but that is the signal which is not readable, and you see that is not really a signal. Anyways, now let me go over to dBm, because then it is much easier to read. And here we are at dBm, and that is minus 123 dBm, so that is where we should already see a 12 dB SINET. Okay, and now let's increase here our level until we reach finally down here our 12 dB. Let me increase a little bit here the audio level. So here that is the audio level. So 200, 300 millivolt is fine. And well, you see yeah. So what we can see is that around here, I mean, it is still a very weak signal, and therefore you see that of course our sinus is not stable, but now we are almost at 12 dB, so that means we need a level of minus 113 dBm to reach finally here the required specs. And that means that we are Yeah, so we are 10 dB, so we lost 10 dB, and that is huge. But on the other hand, I have been told it is on 70 meter and 2 meter. 10 dB is not so much that I would expect that there is something wrong with the first RF transistor or such, or that there is maybe a protection diode blown or such. So 10 dB is a little bit different. So normally if there is something, if there have something happened heavily on the front end, then we would see a loss of 30-40 dB. So that is more what we see if there is a transistor blown or such. Here 10 dB is definitely different. So let me go over to 70 centimeter and let's check there as well. Okay, and now we are over at 70 centimeter, and according to our specs we have seen that we need to dial in 0.2 microvolt, what we have done. And again, also on 70 centimeters we are not able to get the needed output. And so we do exactly the same here. Let's switch over to dBm, simply because it is easier to read. And here we have minus 121 dBm, which represents 0.2 microvolt. And now we do here exactly the same. So we increase our level until we are maybe stable. Let me see. Maybe somewhat here it might be stable. So the loss is obviously not that high here. Here it is, what is it, 6.5 dB what we have lost. So, and that again tells me that the problem must be somewhere different. So I do not really believe that it is in our front end. Maybe, and well, it is only a rough guess. So maybe something is wrong here with the ceramic filter. So that is one point where I would look first to see, have we a problem with the ceramic filter. So I'm talking about the 450 or 455 kilohertz filter. So maybe that is the indication that this filter is going to make trouble. So that is what I'm interested first to see what the filter is doing. And here we have the schematic to understand what I'm talking about. So down here we have our IF amplifier transistor, and we are here already at 455 kilohertz. Maybe for the first step we go here over to our block diagram, so that might be a little bit more easy to understand, because that is here our IF amp, and sorry, it was not 455 already. So that is here our 47 megahertz, okay? And then we have here our IF amp, and that is here already the FM detector, if you like. Of course, so we have here a mixer inside, and what you can see here is that it is a 450 kilohertz filter, ceramic filter. So you see that it goes here through our filter back into the IC, and then the detector for finally FM. And on the other hand, you see that behind the filter, our 450 kilohertz signal is taken as well for AM. So I mean, we do not have really AM, but in the States and somewhere else, so there are also AM frequencies for radio amateurs. But on the other hand, so we have some other bands here which we can receive on AM, and of course therefore we need as well here our AM signal pass, and therefore we have of course both going through the same signal pass, so 70 centimeters and of course 2 meters, and everything will finally get here to our Q1044. That is now what we can see here again better. So our IF transistor, then we have here inside the last mixer to get down to 450 kilohertz, and you see here it gets out through the filter. Here we have our pick for AM receive. Here, by the way, is the AM diode, so that is the AM rectification or AM demodulator, whatever you want to call it. And then if not AM is the path we are looking for, it goes back here into our IC, where we have of course our FM detector. And therefore we can easily see if up to pin 16 of our IC the signals are fine. And what we can see here is that at pin 16 we should have here we have the different frequencies, and we are first interested in 146 megahertz and of course 440 megahertz. And you see that Yeasu was so kind to gives us here the levels, which is very, very nice. So thank you very much, Yeasu. So that makes it a little bit easier. And so we can say, when we have taken here this test, if up to pin 16 is everything fine or not. If it is fine, let's say that we really can see at pin 16 on 146 megahertz plus 10.4 dB, and be careful, so that is dB microvolt. Again, another way of expressing signal levels. Okay, so that is here in dB microvolt, and therefore we check if we have this level here at 16. If the level is really at positive 10.4 dB microvolt, then we know and we are sure that everything in front of pin 16 is simply fine, no problem. And then we have to check what's really going on here at our filter. And of course, so that means that our next step is to crack the radio open, to get to our Q1044, to probe down at pin 16. Alright, and our radio is out of the housing, and I've already prepared here the test setup, and I'm feeding in a signal into the radio so you can hear it, so that is fine, but it is now interesting to know if our filters, especially the ceramic filters, are working. And here we have our 450 kilohertz filter, so the second IF, and we know that these filters are sometimes really a problem, and my suspicion was that well, when we are losing 10 dB overall, so that is what we have recognized first, that I mean 10 dB is on one hand quite a lot, but on the other hand it is not that huge, so you know, it is not really telling that something goes wrong dramatically. Okay, so let me call it that way. And so therefore my suspicion was that maybe here our filter is starting to go bad. And I've already checked it a little bit, and I have compared it to the data sheet, and what I can say so far is that here from the input of the filter to the output of the filter we have approximately 8 dB loss, and that is definitely too much, because normally we would expect 4 to 5 dB what this filter attenuate signal, so that is normal, right? But 8 dB is already a little bit too much, so therefore I would assume that this filter is going to be bad, but that does not finally explain where we lost you know, our 10 dB overall. Yeah, and what you can see here, so that is the input into our 450 kilohertz filter, and you see it is minus 40 dBm approximately. And when we now swap or go over, so let me try to the output, so you see it is almost minus 48, which means we are 8 dB, or we have 8 dB loss down here in our filter, and that is definitely too much. So I'm 100% certain that this filter is starting to die, but it is not, you know, it is really not the only what's going wrong, so there must be another issue as well, and it might be that we can improve the signal a little bit by aligning the front end. So that might be definitely a way to improve our sensitivity. So maybe that we go and check that next, if you know, we can improve it by simply aligning the front end input stage. And let's check the schematic once again, so that we all understand what we have done. So the last test what I've showed you is that we tested here the input of our 450 kilohertz filter, okay, and we have seen that was approximately minus 40 dBm, and then we tested at the output, and we have seen that it is so that it was approximately minus 48 dBm. So that means that we have loss here in our IF filter of about 8 dB. And that is definitely too much. So I would expect to have here maximum 5 dB loss here in our filter. So that is definitely telling that something is going wrong. But additional to that, I have tested here as well our 47.250 megahertz filter. So that is our first IF, and here is our first IF amplifier. And so I have tested what the filter attenuation is here with this, what is it, XF 1001, and that filter is really attenuating 5 dB, what is fully in spec. And then we have here our IF amplifier, and this amplifier amplifies by 16 dB. So when we have at the input of our transistor here, we have minus 73 dBm, okay, and at the output of the transistor we have minus 57, okay. So that is 16 dBm of amplification. So we know that that filter is fine, the IF stage is fine, and finally here our detector circuit is working as well. But the attenuation here at our ceramic filter is definitely, let's say 3 dB approximately too high. So the attenuation is too high. So therefore that is what we have done, and that is what we have found. And now, as I said, let's go back and let's try to align according our service manual. Let's align the input stage, so the front end and the IF and whatever is combined with this alignment. Okay, first, so we found that here our filter is, it is not really good, so the attenuation is too high, and we swap out the filter here first, and then we can put the radio back here in our housing to be able to perform a good alignment, because you know, we really should have that new. We should have the radio inside the housing, that we have all the needed shielding, because all the material here is of course shielding, and that is really needed to perform a good alignment. So okay, let's start here with swapping out our filter. Okay, and getting here the filter out is always a little bit critical, because you see we have really high density here on both sides here of our filter, so we really need to work very careful that we do not destroy components or the PCB itself, or that we do not really blow components here of our PCB, so that all would be a real horror if that would happen. So let's go step by step and very carefully. And therefore, as you can see, we have here our preheater, which will rise the temperature of our PCB and of course of the components on more or less the same temperature level, which is really important because we have different materials used, and if we really heat it all too fast, then all the materials work different on different temperatures. So we really have to do that very, very slowly, therefore here the preheater is in place. We start to preheat it, and then let's see how we move on. And as discussed, I now start here the preheating process. So that will take, of course, a while. And when we are going the next step, I will be back immediately. Okay, so then let's go ahead. So we should have now a nice temperature here on our PCB, which will certainly directly activate here our flux. And as always, we put some fresh solder to the solder joints, of course. Okay. Very nice. That is fine as well. And of course, that was the last one. Alright, so let's see what we can do here. And as you can see, as expected, it is really not so easy, even with preheated temperature. Okay. But now we have it. That is good. And as I can see, we have kicked out a little capacitor which we need to get fixed again. But other than that, it was quite good, so without any bigger damages. Okay, so as you can see, our component is out, and pads are clean, and everything is nice. Here our little capacitor is back in again, so that is fine as well. The next is to place our new component. And of course, here out of my stock, I have this SMD IF filters, 450 kilohertz, and of course we need here a new one, which we have here. And now, yeah, let's go and put it in. And as you already can see it, it is already prepared. so that we really can try and place our ship. It is a little bit difficult here at this site since we have ground plane here, and yeah, therefore that is a little challenge to get it done here. Let's see if it is not tacked. So yeah, that is exactly what I meant. Okay, so it is tacked, and now we need to get it tacked to the other side here, and then we can go ahead. Okay, so we have done the right side. Now we have to do here the left side of the pins. And of course we take enough flux, then let's see, and as always, don't rush. That does not make any sense. Okay. Okay, looks pretty nice. Both contacts are done, and then our final is here. So both are ground, so that's what I meant. When I said we have here a lot of ground plane to overcome, so therefore again we need to heat it here a little bit more as usual. Yeah, looks good. Okay. Now we have to clean it, and then I would say job is done. As long we are talking here about soldering, so let's once again check the other bows. And you see that is fine. So now let's clean here our contacts. Okay, so let's control our solder joints, and yeah, I would say that is just fine, no problem. And here on the other side it is the same, so both solder joints are fine, and as far as I can see it, clean and no problem, all is fine. Okay. Okay, so everything ready so far. Now we put it all back here in our housing, so that we can finally do our alignment, and then job should be done. So okay, after we have replaced our IF filter, we are already testing, and I am here on the 70 centimeter band for 35050 megahertz, and radio is receiving, as you can hear. And yeah, I'm really amazed because the receive here on 70 centimeter is already good after we have replaced our IF. So let's have a look to our meters. Okay, and have a look. So we are sending with minus 123 dBm. So I'm connected to the upper one, so here you can see it, 435.050 minus 123 dBm, right? And we are reading down here our SINET. And what you can see here, that with minus 123 we are already exceeding the requested 12 dB SINET. So you see, of course, it is jumping because we are in the noise, but we are always above our 12 dB, and that is clearly showing that we have already a little success. But what we want to do is to line our radio. So that is what we set. If the IF filter is replaced, then it makes sense to go after the alignment, and that is the reason why it is connected to my upper tester, because now I'm transmitting into it, and I can read the frequency up there. So now in this camera position we can really see both. So first of all, the transmitted power into the radio, the frequency, and now let's check if I go here into transmit. So let me go and press the PTT, and I cannot do it. Why can't I do it? So hang on a second. Hang on a second. Yeah, I have to replace it here, sorry. Okay, so now we should be able to do it. So as I said, we expect to get 435.050 here when we transmit on our counter, and let's see what we get. So first of all, you see we are transmitting with half of a watt, which is fine, and then you see on the counter 435.049.708. So that means that our reference is not where it should be. So that means we need to align our reference oscillator, because you see, and while I am transmitting, it is getting worse. So that means our transmitter frequency is lowering, as you can see, and that means that our reference frequency inside the radio is not really adjusted. So everything we do with this radio is that we have to do it via a menu. So all is done by software, or all have to be done by software, so there is no pot or anything. So that means we have to go into the service mode and then into the service mode, and then we can align our reference oscillator, and that will be, of course, the next what we want to do. And you see now we are almost 400 kilohertz off, so the frequency is too low, and of course, and you see it is dropping, it is still dropping, and even we are only transmitting here with half of a watt. You see the radio is getting hotter and hotter, and the frequency is running away. So that is far too much, and we need really to get it back to the right frequency. So let's go ahead. Okay, so first of all we have to set the radio into our alignment mode, and therefore first what we need to do, we have to press both buttons here together, which is already a little bit difficult because the camera is in front of me. Okay, I try it, let's see. Then we have to switch it on, and you see it goes into a menu. Not sure if you can see it. Yeah, let's try it. So now I have to go where there is nothing on the display, and now I have to follow exactly this button combination. 1, 2, 3, 4 and 5. Yes. So now we are in the alignment mode, and now when I press F here, we see that the menu, I hope you can see it. I do it again. So you see now we are in alignment procedure 0, all right? And I directly, and you see here reference 99HA, and of course while I am pressing here my I have to go ahead within a couple of seconds, so I press it. Now I need to go into transmit, and now I see the frequency on my counter, and I can adjust here with my dial, and you cannot see it here, but I can adjust the frequency to the right position. If I leave it here, and if I do it here again, start, press, and now I can align the frequency. So that is a little bit tricky. So now you've seen how I have to do it here, and let me go over to the counter that I can show it to you. Okay, so you see the counter, and I do here now exactly the same what we have discussed. Now I transmit, and you see we have a frequency, and you see that we are, and the problem is I have to do it always once again. So let's see what we have. Let's see that we really get to as close as possible to what we need. And the problem is that the radio is a little bit moving, since the radio is getting hot, and therefore I cannot get good and easy reading over there. But you see, now we are only 13 hertz off, which I would say is fine. And you see it is dropping a little bit, so therefore let's say that this is already nice, and that means that now our reference frequency has been aligned, so that is done, and we need to go with the next step. And now I have prepared everything for the next step, which is RF front-end tuning. So that is simply the sensitivity. And according to our service manual, you can see that we have to align our radio to 439.050, and then we have to set a deviation to 3.5 kilohertz with 1 kilohertz of modulation. So, and that will be the frequency where we align the front end for maximum sensitivity, and we do it by putting in a level of plus 10 dB micro, and we have to adjust for the highest DC voltage. So this alignment will be done with DC, and therefore we have again to prepare everything to be able to align this here. Right, and here you see all the parameters we had to dial in. So you see here the deviation, that is the modulation, you see the input level, and you see the frequency. And what we have to do now is to align our value with the DC voltage we are picking here at the respective test point. And the test point is here one little pad where we can pick our DC, and this DC is proportional to the radio sensitivity. And of course the question is, how is that possible? Well, that is quite easy. You can always use the AGC, so the automatic gain control, for doing those alignments with DC. So normally you would do it over an output meter, so that means you would monitor the output voltage from the speaker, and you can of course align your radio also with the output meter, which is not more than an AC voltmeter, which is able to pick this voltage, and you can then use that as a reference and align it as well. In this case we do it with the AGC, which is another way to do it. It is more or less the same, and the outcome is more or less the same. So therefore here it is described with DC, and so we do it. And when I go down here to my test point, which is here, you see the 1.39 volt, which is now the AGC. And what I'm doing, I try to align for the maximum AGC with this input parameters to be able to point really the front end to the maximum level. So that is what we do. And I've already done it, so it is a little bit difficult to show it here while I'm doing it, because I really have to do many things simultaneously. So I have to pick it, and I have to set the radio itself into alignment mode for in this case 70 centimeter, and then you put, of course, your probe down here to the test point, and then you start to aligning for the maximum DC. So that is basically the same what we have seen when we align the reference oscillator. So we set the radio into alignment mode, we press our PTT, and then we start aligning for our 435.050 megahertz, which was the frequency which was announced here in our service manual, and we tried to align the frequency as best as possible to our counter. So with the sensitivity is more or less the same, but as I said, it is a little bit difficult to do it with camera, but I guess you got the idea. And I do now exactly the same, of course, here for 70 centimeter, and then I switch over to a 2 meter, and I do exactly the same on 2 meter, and then the front end is aligned, and that means that we have obtained the maximum possible sensitivity for the radio. So that is what it is after all. Alright, and we have done now exactly the same on 2 meter, and I have set the generator to 160 microvolt, so that is exactly what we have in our manual. So with 0.16 microvolt we should be able to get 12 dB SINAT in or between 140 and 150 megahertz on FM. So you see that we really are able to get that. I mean, sure, we are still a little bit in the noise, and that is maybe I can switch on here this speaker. So I believe you can hear that. So we are really still in the noise because 0.16 microvolt is really a low signal. But anyways, we are able to be within our figures, and that is quite nice. So that clearly shows that replacing our IF filter, where we had a big loss, which was too much, and aligning the front end finally solved here our problem, and you see that it is now more or less stable. Okay, and we are getting here to an end. So alignment has been done, and we have improved our sensitivity. So radio is now back in nice order, and we put it now back together, and then this job is done. Okay, and that is then here our last picture. So radio is ready and back together, and finally once again, so you see we have our our negative 123 dBm, and you can clearly see that we are easily above 12 dB SINAT, which is really nice. So that's it. We really can give this radio now back to its owner. And of course the radio transmits as well So everything is really nice, and you can hear it here over the speaker. So the tone is still clear, even we have only minus 123 dBm here, and that clearly shows that it was a good idea to replace the broken IF filter. And so we are really now at the end of the video. Thanks for watching, and catch you next time. Bye.